In this video, I'm going to discuss dimensional modeling. Dimensional modeling can be done using a relational database. It's meant to better support real-world data techniques. Therefore, it's not a strict model, but rather allows flexible table organization to support how the data will be consumed. Dimensional modeling handles complexity well and strives to improve read and write performance. Its goal is to be suitable for real-world data scenarios. Therefore, it's a practical modeling technique. Dimensional modeling breaks the data into two separate concepts. Measurements, for example, if data is being read from a physical thermostat, the thermostat reading at any given point in time is a measurement. And context, which is the useful information related to the measurement. So for instance, the thermostat might have a manufacturer and an age, and these might be stored as context for each measurement. So the first one we'll talk about is measurements. Measurements are often numeric values, although they don't strictly have to be. Some physical devices, for example, have measurements that are states. For example, high, medium, and low could be state measurements. But usually measurements are integers or floating point values, such as temperature measurement. Measurements are taken on a continual basis, say once every 10 minutes for a thermostat. Each measurement results in a new value. Another term for measurements is facts. Facts are values that are very specific and well defined. For instance, the thermostat temperature measurement, or fact, at a given point in time was 67.3. Context, often textual, although it can also be numeric, needs to be included to make sense of the facts. For instance, what is the measurement of unit? In the case of the temperature, it may be degrees Fahrenheit, and this is context. The manufacturer of the thermostat is another piece of context that might be useful. The minimum and maximum possible values for the thermostat are additional pieces of context. Fact context is flexible and detailed. Its format is not as strict as a numeric fact. It can even be sentences or paragraphs of text. So how should you store context? While it would be possible to store all of the context for a fact as one object, say as a large text object, it's beneficial to break context into logical groups called dimensions. For instance, in our thermostat example, the thermostat manufacturer name may be one dimension. Unit of measure may be another dimension. These dimensions can be treated as independent, although in fact they're often not completely independent. As an example, consider that the minimum and maximum temperature readings for a thermostat may be dependent on the manufacturer. All thermostats of a particular manufacturer will likely have the same temperature range. There are also some dimensions that facts are highly dependent on. A perfect example is time dependence. For the thermostat example, temperature readings are of little use if they're not paired with the time of day that the measurement took place. How do you model measurements or facts? Facts can be stored in a single table, although they could also be broken into separate tables. Let's assume you have facts that are stored in a single table. There may be several other tables containing the context or dimensions for those facts, and all these tables will usually have a many-to-many relationship. For the thermostat example, consider thermostat manufacturer and thermostat serial number as two dimensions. One manufacturer will represent many thermostats, which will have readings at many different times. So this is organized as fact tables that have multiple foreign keys to different tables that store the fact's dimensions. The dimensions, or contextual entities, such as thermostat manufacturer, have a single primary key that's mapped as a foreign key in the fact table. So manufacturer ABC of thermostats may be a record in a manufacturer table with a text field for manufacturer name that's ABC in this case. And that record has a primary key, say 1234. In the fact table of all the thermostat readings, Each reading might have a foreign key for thermostat manufacturer. Those values that are read from thermostats of manufacturer ABC would have the value 1234 in that foreign key, so you could join the model context to the fact. You should break fact data up by grain. Grain can be thought of as dimensionality, or put another way, what does each record in the table represent? Only records of the same grain should coexist in the same fact table. In the thermostat example, you may read instantaneous temperature every 15 minutes, but you may also store daily temperature averages. Now these are different grains. You wouldn't store instantaneous measurements with daily averages, because they don't represent the same thing. They would be stored in separate tables. Generally, you want all dimensions to be used for all facts in the table. This boils down to having a value for every foreign key to the context dimensions in the fact table. Following these rules reduces the chances of errors. For example, you could store instantaneous and daily average temperature data in the same table, but if you went to perform analytics on the data, you could accidentally combine the two and get erroneous results. When designing fact tables, you should consider how facts are going to be combined, because facts are usually queried in groups and then aggregated. The most common type of aggregate on facts is additive. Therefore, if possible, store facts in an additive format for simplicity. Consider a system that keeps track of people buying tickets at turnstiles. By counting the people going through the turnstiles over time as one dimension, and the ticket sales at the turnstiles as another, you don't have to store ticket cost, because you can add the number of people and the ticket sales in a given time range and simply divide to get the cost per person, or the price of a ticket. Semi-additive facts are facts that can't be easily derived by adding other facts. In our thermostat example, the temperature level for a range is not easily additive. That is, you can't derive it simply by adding the temperatures together in a range. Instead, you can make it semi-additive by adding the temperatures together, say for an hour, and then simply dividing by the time range. This gives you an average and is also called averaging over time. A special type of fact table that oddly enough contains no actual facts is the event. Events are purely contextual and take place at a moment in time. For instance, a fact table might keep track of the time a server crashes. There will be contextual data around each server crash, but no actual facts, because the implicit fact is that the server crashed, which is the event. Events are valid to store as facts tables with only foreign keys to contextual dimensions. And finally, there's the concept of degenerate dimensions. This is a situation where a facts table holds children of a parent entity as the records, but the parent entity itself has no contextual dimensions of its own. In the thermostat example, if thermostats were routinely queried by manufacturer, then manufacturer might be a degenerate dimension. The degenerate dimension has no context because it's been removed or moved down to the child. For instance, dimensions like minimum and maximum temperature readings could be context for a thermostat manufacturer. But if the grain or meaning of the records in the facts table is a thermostat, then minimum and maximum readings would have moved down to be contextual to each thermostat. The element, or in our case the thermostat manufacturer, is then left without any attributes of its own. Degenerate dimensions are typically added directly to the facts table as their own column. So the thermostat facts table would have a column added from model manufacturer. In this way, thermostats can be grouped by their parent, or thermostat manufacturer in this case. In this video, we're going to look at a form of data organization called the hierarchy. Hierarchies organize data into levels that make it easy to identify trends in the data. For example, imagine a hierarchy of stores, and one level of the hierarchy was area, each area containing several stores. Low sales figures in an area might indicate a trend in this area. They also allow a drill down into lower levels that exposes reasons that explain the trend at the higher levels. So in our example, one might drill down into the area with low sales figures and look for clues in the sales figures of the various individual stores. And trends at lower levels roll up to higher levels, so lower level trends can predict trends at the higher levels. In our example, several low sales figures at the area level might indicate that the level above area, which might be country, is going to show low sales figures as a result. A hierarchy is built of levels. There's a base level that's the most detailed level. In our previous example, the lowest or base level of the hierarchy for sales figures might be even lower than the individual store. It might be a level of individual store departments. As you go up from the base level, level values consist of aggregates or combinations of values from the level just below. So for example, the level above departments may be stores, since sales from several departments are added together to give the sales figures for each store. Area might be above store and consists of the total sales of several stores under each area. A hierarchy's levels have a parent-child relationship. In our example, a department is a child of a store, and likewise a store is the parent of a department. An area is a parent of a store, and a store is a child of an area. So what is the relationship of hierarchies and levels? It's a many-to-many relationship. As we've already talked about through our example, a hierarchy can contain many levels that contain different structures. In our case, country, area, store, and department. A level can also exist in many hierarchies, and in this way hierarchies can be interrelated. In the context of a database, one can create dimensions that are hierarchical. We could consider our store example as a dimensional hierarchy called region. It's defined as having several substructures, country, area, store, and department, that create a hierarchy that together represents a region. The dimensional hierarchy has mathematical relationships that define how aggregations work. For instance, sales totals are summed up as you move up the region hierarchy. These associations between members can be used to query the hierarchy. For example, you could query for the total sales in Canada, and it should sum up all the total sales in the areas, stores, and departments under Canada. For a dimensional hierarchy in a database, dimensions are the dimension types, in our example region, and the members would be all the levels below the dimension, in our example country, area, store, and department. Hierarchies have the concept of siblings, which are nodes that are at the same level in the hierarchy and are directly associated under the same dimension or member. In our example, all of the stores in an area, say area A, would be siblings, since they're at the same level, they're all stores, and they're associated to the same member in the level directly above them, area A. Note that it's important they're associated to the dimension or member directly above them, and not several levels above them in the hierarchy. So for example, all stores under the country Canada are not necessarily siblings, because they belong to different areas. Finally, it's important to understand the parent-child relationships in the dimensional hierarchy. all the members of a dimension are called children of that dimension. In our case, country, area, store, and department would all be children of the dimension region. And members of other members are called children of that member. So in our example, departments are children of stores. Note that departments are not children of areas because they're not direct members. In other words, a store contains many departments, but an area does not contain many departments. It contains many stores. So stores are children of areas. In this video, we're going to look at strategies to handle slowly changing dimensions. Slowly changing dimensions are a common technique used in data warehousing, where dimensional change is captured over time for dimensions that are not changing very often. Consider, for example, the temperature set point on a thermostat unit, which is set by users of the thermostat to whatever temperature they would like the thermostat to achieve. Now imagine you had a system that was reading, among other dimensions, this dimension of set point. This would likely be considered a slow changing dimension because it's not constantly changing. It only changes when someone decides to set it, which might not happen for days or months. The first strategy we'll look at for managing slow changing dimensions is called type 0, or retaining the original value. This is only useful for dimensions that never change at all. So this wouldn't be useful for the previous example because a thermostat set point does change. You can group facts or measured values by these dimensions because they're original values and they never change. They're constant. Any attribute that has original at the start of the name is probably a candidate for type 0. For instance, if we had an original set point for our thermostat that served as a baseline. Date and time dimensions often fall under this type. For example, if a temperature dimension fact is read from the thermostat, it will have a timestamp that's not going to change moving forward. Next is type 1, or simply overwriting the old value with the new value. Unlike type 0, where the dimension value never changes, this facilitates updating your dimensions. It's also efficient for storage, because once a record is written, it never grows. It's simply updated. The downside is that there's no history stored. This would be useful in our thermostat example if history of set points was not an important detail. Next is type 2, or adding a record. In this strategy, when the dimension value changes, a new record is added to the facts table that contains the changed value, and the original record is set to inactive. This is more complex than type 1, but it has the benefit of history in the facts table. The active records can be queried to see latest values, and the inactive records still exist and can be queried to determine values of the dimension at any point in the past. This is useful for historical reporting, where one wants dimensions to report what value they were at a specific time in the past. Next, we have the type 3, or add attribute strategy. Sometimes also called the alternate reality strategy, because it offers the ability to query two alternate versions or realities of the data. This strategy adds a column to the facts table that's used to store the old value of the dimension when it changes, and the new value overwrites the old value in the original column. In this way, two values are maintained, the new value and the value just previous to it. This type is rarely used because it's complex to implement compared to the benefit, which is simply to keep the last value. Then there's type 4, or adding a history table. This can be efficient for dimensions that have quickly as well as slowly changing attributes, or if the attributes are queried often, because it splits historical records into a separate history table, leaving the original dimension table with only the latest records. This is efficient for querying because it separates queries for latest dimension values and historical queries to different physical tables. The historical table requires the generation of a unique primary key called a surrogate key. This strategy also often involves breaking fast-changing attributes into what's called a mini-dimension in a separate table from the slow-changing ones. Keys to both the dimension tables are then kept in the facts table. This is a very popular form of dimension management that you'll see implemented in some fashion by many commercial data stores. Type 5, which is called that because it's type 1 plus type 4, is very similar to type 4 in that it preserves historical attributes in a mini-dimension table of fast-changing attributes and another table of slow-changing attributes. Like type 4, it allows one to report historical facts with the dimension values that were current for that time. But it also adds a reference in the base, or slow-changing dimension attribute table, that references the latest record in the mini-dimension or fast-changing attribute table. This is basically for query performance, when the mini-dimension fast-changing table has a lot of rows and therefore querying the latest records would be slow performing. And finally, we have type 6, which is type 1 plus type 2 plus type 3. This type uses type 2 behavior, which is to create a new record every time attributes change, and marking the most current record as current while setting the old records to not current. But it also includes type 3, where an attribute is added that stores the previous or old value. And finally, type 1 is used as the current value field of all the old records is set to the current value. This strategy is not used often, but it does allow for easy filtering and grouping either by most recent attribute value or by historical values. In this video, we're going to look at temporal databases. These are databases in which the data is related to time. A perfect example would be readings collected from Internet of Things devices. Each reading is associated to a timestamp, which gives context. For example, if you're reading power generation measurements from a solar panel, it's important that you know what time of the day each reading took place. Temporal databases use temporal data types, such as time ranges, date-time objects, or simply date objects. Data in a temporal database can represent past or historical data, present data, or even future data, in the case of predictive data, or when the effective range of a particular data value is extended into the future. The main temporal elements usually included in temporal databases are valid time. This is not a single time, but rather a time range. It's the range of time in which a piece of data is valid in the real world, and has both a start and an end time. For example, a rotating solar panel might have been at a particular angle to the sun between 2 p.m. and 5 p.m. on a given day. The transaction time is the time that the data was stored in the database. For example, a thermostat temperature reading might have been read at 5 p.m., but not stored in the database until 5:05, due to some latency getting to the cloud. The transaction time would be 5:05, or the time it was physically inserted into the database table. And the decision time is the time that a decision was made about the data. This is often equal to the start time of the valid time range, but not always. For an example where it isn't, imagine a database keeps track of a person's pay rate. If they received a pay raise on July 20th and immediately began receiving that new pay rate, then the start time for the valid time range and the decision time would be the same. But what if the pay raise was retroactive? Then the decision time would be the time the raise was decided, July 20th, but the valid time of the new pay rate might start back on July 1st. There can be degrees of temporality in a database. A non-temporal database is one where none of the tables are temporal. That is, they don't store data associated with any of the temporal elements we just looked at. A partially temporal database is one where some but not all of the tables are temporal. This can represent a temporality somewhere between 0 and 100% exclusive. This is a very common scenario. And finally, a database can be fully temporal, meaning every table in the database stores data with temporal elements. The data in a database that's either partially or fully temporal can be unitemporal. This means it only has one time dimension. This would be either the transaction time or the valid time range. Or it could be bitemporal, where two dimensions of time are used. These are valid time range and either the transaction time or the decision time as a second dimension. And finally, a tritemporal database stores all three time dimensions: valid time range, transaction time, and decision time. The more time dimensions a database has, the more flexibly it can be temporally queried. There are two types of temporal table, based on how they can be queried. An effective temporal table is one where the data can be queried based on when the values were effective in the real world, but not necessarily when they were entered into the database or their transaction time. Any tables that have the valid time range or the decision time dimensions will be effective temporally. This is usually the most useful type of temporal table. To explain why, imagine you have a service that tries to maintain the temperature in a room by reading the current temperature, then sending signals to adjust the air conditioning unit. Should your service logic care about when a temperature reading was effective in the real world? In other words, in the room itself? Or when the value was inserted into a table? Of course, you would care more about what time it was in the real world when the measurement took place, because when it was written to the table is somewhat arbitrary. There could have been latency between the reading and when it was stored. Tables with entered temporalness are the opposite. They can be queried by when the data was written to the database or the transaction time, and not the valid or decision times. This is typically less used, but can be satisfactory for some applications. For example, a system that records manual comments might be able to use an entered temporal table. So how are temporal tables modeled? Well, there are two main schema. The star schema is a schema where the facts, which are the temporal pieces of data, are stored in one or more tables that reference a set of flat dimension tables for contextual information. The simplicity of the dimension tables aids querying efficiency. And the snowflake schema is similar to the star schema in that the facts tables reference dimension tables, only those dimension tables are not flat, but instead can reference other dimension tables themselves. This allows for more efficient data storage, but leads to more complex querying. We'll look at these schema in more detail now. Let's look at the benefits of these two schema in more detail. The star schema, where dimension tables are kept simple and flat, improves the speed of read queries because the joins required are simple. Basically, every dimension table is represented by a foreign key in one of the facts tables. So the deepest level of joins there need to be is 1. The less complex the query is, the more performant it is. So if you simply want to read facts and their associated dimensions, and have no other more complex queries to perform, then the star schema is likely to meet your needs. Applications that simply trend the facts and associated dimensions are prime candidates for this. The snowflake schema, on the other hand, trades simplicity for a lack of data duplication, as well as flexibility in queries. In this schema, the dimension tables can themselves break down into multiple tables joined by keys. It's called the snowflake schema because, unlike star schema, in which the tables, when drawn in a diagram, resemble a star with facts tables in the middle and one layer of dimension tables around them, the snowflake schema explodes the single layer of dimension tables into multiple layers, just like a snowflake grows more complex from the center. The snowflake schema is good when you have more complex query needs and you want to be able to select subgroups of the dimensions for facts. Snowflake schema also minimizes data duplication, since the dimension tables are normalized, meaning that when values are repeatedly referenced, they're broken out into a joined table. For example, if the thermostat readings are stored as facts, and the dimension table has attributes manufacturer and model in a flat table, then manufacturer names are inevitably duplicated because there are several models associated with a manufacturer. In Snowflake, the manufacturer can be broken into its own table with only one record per manufacturer. Then the multiple models for a single manufacturer can have a foreign key to the manufacturer record, instead of duplicating the name. This saves space, since a foreign key is probably smaller than the name as a string. But this complexity of multiple joins causes reads to be less performant. So Snowflake is best when you need flexibility in querying dimensions and you're willing to take a hit on performance, such as with more complex data analysis. So to summarize, the star schema is appropriate for data marts, which are subsets of a data warehouse that have a limited, specific focus to the data, such as data used for simple charting. Whereas the Snowflake schema is suitable for wider data warehouses that might store data for multi-purpose business analytics. Star schema are not normalized, meaning they duplicate data, whereas Snowflake schema has normalized dimension tables that avoid data duplication. Due to data duplication, star schemas tend to take up more space, but in turn are less complex to query. Snowflake schema take up less space because of normalization, but are more complex to query due to the multiple joins. Star schema tend to be faster to read, and the SQL queries involved are simpler because they only have one level to join. Snowflake schema tend to be slower to query, and their SQL queries can be more complex, involving joining of various dimension tables. Here is what goes into a star schema. You separate your numerical data, or facts, from descriptive data, which gives context to those facts. So for example, if you were reading temperature measurements from a thermostat, the raw measurement as a double would be the fact, and the descriptive values, also called dimensions, might be thermostat manufacturer, thermostat model, and units of measure, such as Celsius or Fahrenheit. The facts then go in one or more fact tables. Each record in a fact table should contain fact attributes that are queried together. In our example, we might have a thermostat fact table, and it may contain several attributes or facts about a thermostat reading, which are taken together, such as temperature and set points. The dimension tables should also represent dimensions that are naturally grouped. In our example, there might be one dimension table called thermostat dimensions, with manufacturer and model, and another dimension table called units dimensions, with units of measure. In the star schema, these are flat tables with only one primary key and no foreign keys. The fact table is connected to these dimension tables via a foreign key. So our fact table might be called thermostat. The attributes might be temperature, which is our fact, then a foreign key to the thermostat dimensions table, and another foreign key to the units dimensions table. So what are the advantages of a star schema? First, the queries for a star schema are simple. They always involve querying for the facts, and then one or more first-level joins to the dimension tables as needed. These queries are efficient because there are no nested joins. The dimension tables are all flat. You can get to business insights quickly because these schema are performant. Online analytical processing, or OLAP systems, allow the use of star schemas to build OLAP cubes, which represent raw data and aggregated data. Some disadvantages of star schemas are possible degradation of data integrity. Data is duplicated, and whenever data is duplicated, there's the possibility of error. For instance, say a star schema contains a dimension table with temperature units as a field. Now with inserts, one person enters the value Fahrenheit spelled Fahrenheit, but another person inserts a wrong spelling, say Fahrenheit. A star schema does not stop this, so it looks like there are two different temperature units, when in fact there's only one. You can't model many-to-many relationships in dimensions with star schemas. For example, imagine your fact is the temperature readings from a thermostat, and your dimensions are model and manufacturer. Now imagine a model of thermostat may be created by a collaboration of more than one manufacturer. With star schema, there is no way to represent this, because there can only be one value per dimension for a single fact value. Star schemas don't lend themselves well to flexible, complex queries, like you may use for more advanced data analysis. Now, let's consider what goes into a snowflake schema. Where star schemas are one-dimensional, they don't allow nested joining of tables. Snowflake schemas are multidimensional, in that they allow multiple nested joins. To create a snowflake schema, you basically create a star schema, but then divide the dimension tables into multiple tables joined by foreign keys. This results in an exploding out of the dimensional tables, adding complexity like the complexity of a snowflake. When dividing dimension tables, you want to normalize any denormalized data. Denormalized data is data that's repeated in a field of the table. For example, if you have the fields model and serial number in the same table, and several serial numbers can be of the same model, then model names in the model field will be duplicated. Instead, break this into two tables, model dimension and serial number dimension. Each record in the serial number dimension table will have a foreign key to the model dimension table. Then the model dimension table can have only one record per model, removing the duplicated model names. And multiple records in serial number dimension can have a foreign key to the same model dimension record. Snowflake schemas lead to efficient data storage, since they minimize data duplication through normalization. OLAP modeling tools can consume Snowflake schemas for data analysis. Some disadvantages of the Snowflake schema are the complexity of the schema and resulting complex queries with nested joins. We discussed how the star schema can reduce data integrity, while Snowflake schema have better data integrity because they avoid duplication, and therefore the possibility of errors such as misspellings and strings. You still have to make sure the data going into the schema is high quality, or data quality will be reduced. For instance, you can still misspell a string in a normalized table. This Snowflake schema is not great for cube data processing, which is more the realm of star schema. This is because the complexity of multiple joins slows down the processing. So how do you design a star schema? You're going to define your dimension tables, and you'll also define fact tables, which have foreign keys to those dimension tables. And you will want to ensure your dimension tables are flat, or in other words, have no foreign keys to other dimension tables. This results in the star shape of fact tables in the center, surrounded by dimension tables, each connected to a fact table via a foreign key. In the following slides, we'll dig into these 3 steps in more detail. First, let's discuss defining dimension tables. Dimensions are descriptive. They describe facts. An example is if you're reading a temperature measurement from a thermometer, the measurement is a fact, and a dimension might be unit of measure or thermometer model. The dimension gives context to the fact. It's detail that someone might want to filter on or show along with the fact on a chart. You don't want to store all dimensions in one huge table, because that's inflexible and very difficult to manage. Instead, you could break the dimensions up logically. For example, dimensions to do with the thermometer itself, such as model and serial number, might go in one dimension table, and units, such as unit of measure, might go in another. As for defining the fact tables, the names of fact tables should describe actions or purpose, often business-oriented. For instance, sales is a name of a fact table. It makes clear what the table is for and what types of facts it stores. Our thermometer example is not really business-oriented, but it could be called room conditions, which describes its purpose, to reflect room conditions through facts like temperature. A fact table combines facts that logically fit under the action or purpose. For instance, the sales table may hold facts such as monthly sales figures. The facts are values, and they're represented by the fields in the fact table. They can be aggregated for analysis and reporting. You should flatten dimension tables as much as possible, because the star schema means that there are no foreign key relationships between dimension tables. So combine dimension tables where possible to achieve a flat dimension, meaning the dimension tables have dimension fields only and no foreign relationships to other tables. But do keep in mind that a dimension table should represent the dimensions of a logical entity and not several entities. For instance, if you have a thermometer dimensions table and a voltmeter dimensions table, because thermometers and voltmeters are 2 completely different concepts, you don't want to combine them. So, some final points on star schema. It's not a good idea to have all dimensions in a single table, even if it seems like it would be easier. This can be a management nightmare, and it's also inflexible. You should not expect actions from your dimension tables, which means your queries shouldn't treat the dimension tables like a target. The target data you're querying for should be your facts, and the dimensions are simply additional description or context for those facts. If you find you're trying to query dimension data and filtering on facts, then you need to reconsider your design. And don't flatten fact tables like you do dimension tables. It's perfectly normal to have multiple fact tables in a star schema design. Each fact table holds the facts for an action or purpose, so you don't want to join those since they're likely going to be queried independently. So for a quick summary of star schema, you should have one or more fact tables that make up the center of your star schema if you're looking at it on a diagram. And those tables should have fact fields in them, and they should also have foreign keys to dimension tables. Then you should have a collection of dimension tables that on a diagram look like a star because they surround the fact tables. These dimension tables should only have dimension fields in them, and a primary key which matches with the foreign key in the corresponding fact table. In the star schema, dimension tables should never have any foreign keys to other tables. In this video, I'm going to demonstrate how to process data incrementally using date and time-based folders in Azure Storage Account. So I'm in Azure, and under my recent resources on my homepage, there are 2 resources I'm going to be using. One is a Data Factory version 2, and the other one is a storage account. Let me show you how to create your own. So at the top left, I'm going to click Create a Resource. Now I'm on the New page, and in the search box, I'm going to type Data Space Factory and choose Data Factory from the pull-down. On the Data Factory window, I'll click Create. And on the Create Data Factory page, I'm on the Basics tab. Under Project Details, I'll make sure a subscription is chosen, and then choose a resource group or create a new one. Under Instance Details, make sure a region is chosen. Type in a unique name, and leave the version on v2. And at the bottom, click the Next Git Configuration button. Now you're on the second tab, which is Git Configuration. And the only thing you have to set here is Configure Git Later. Just check that because we don't need a Git repository. And then at the bottom left, click Review and Create. And then at the bottom left, click Create. Now I'm not going to do that because I already have one, but that's how you create your data factory. Now to create your storage account, I'm going to click Home at the top left. Then I'll click Create a Resource at the top left of my home page. Now I'm on the New page, so I'm going to type Storage Account in the search box and choose Storage Account from the pull down. Now on the Storage Account page, I'm going to click Create. On the Create Storage Account page, I'm on the Basics tab. Under Project Details, I need a subscription chosen, and I need to choose my resource group again or create a new one. And then scroll down to Instance Details. And for Storage Account Name, give it a unique name. And then at the bottom left, you can just click Review and Create. And then at the bottom left, click Create on the Create Storage Account page. So that's how you create your two resources. Now I'm going to click Home at the top left of my screen. And so now I'm on my Azure homepage. And the first thing I'm going to do is step you through how we're going to do the storage account. So under Recent Resources, I'm going to click on my storage account. And on the overview on the right-hand side, I'm going to click Containers. And I have two containers set up you see on the right-hand side here, Source and Sink. So what I'm going to do is show you how to move data from the source to the sink. And we're going to do it incrementally by placing files in a folder structure that represents date and time. And so it's only going to incrementally move files 1 hour at a time. So I'm going to click on my source container, and I'm going to load a blob. So at the top left, I'm going to click Upload. And in the blade on the right, called Upload Blob, under Files, I'm going to click the Browse button on the right-hand side. And I happen to have a test file called test.txt. And it's not really important what the file is because we're just going to do a binary copy anyway. So I'll click test.txt in the Open window, and I'll click Open at the bottom right of the window. Now, an important detail here is if I click Upload at this point, it's going to upload this blob into the root of the container. I want it to have a folder structure of a very specific type. So I'm going to click Advanced on the blade. And if I go down on the Advanced section, there's a section called Upload to Folder. I'll click on that text box, and I'm going to fill this in with the year. So we're going to use a 2-digit year. So since it's 2021, I'll put 21, and then /, and then the month as a 2-digit. So I'm going to say 04 because it's April, and then /, and then the day is 2 digits. Today happens to be the 15th, /, and then the hour. Right now, the hour is actually going to be in UTC because Data Factory is going to use a UTC time. It's also going to be 24-hour. So right now, the time is 21, the hour is the hour in UTC where I am right now. And I'll click Upload. So now, if I close the blade and I go over to the left, I see a folder in my source container, 21. If I click on it, I see 04, and then 15, and then 21, which is the hour, and then my test.txt. If I click on my test.txt, details on the right-hand side, and if I click on the Edit tab, fourth from the left, it just has a little bit of text in it. This is a test file. Okay, so if I back up going to the top left, I'll click my storage name. That takes me back to my containers. And I just want to show you if I click my sync container that it's currently empty. So let me click home at the top left. And I'm going to go to Data Factory now under Recent Resources. And on my overview of Data Factory on the right, I'm going to click Author and Monitor. Now I'm in Data Factory. And in the middle of the page, I'm going to click Copy Data. This takes me to a wizard called Copy Data Tool. And it steps me through it. So we're on the Properties on the left-hand side. So on the right-hand side, I'm going to leave it as a default task name. And under Task Cadence or Task Schedule, I'm going to choose Tumbling Window. And under Tumbling Window, under Recurrence, I'm going to say every 5 minutes. Now I could say every hour because we were going to do batches of hours. But to keep this going faster, I'm just going to set it to 5 minutes so that it'll copy what's in the hour folder every 5 minutes. And I'll click Next. Now I'm on the Source Data Store screen. And on the far right, there's a Create New Connection button. So I'm going to click that. And in the blade that says New Linked Service, I'm going to choose Azure Blob Storage and click Continue at the bottom left. And then in the blade, I'm going to scroll down to Account Selection Method. And I'm going to choose my storage account name. That's Storage2256. And click Create at the bottom left. That connects it to my storage account. So under Source Data Store, I can now click Azure Blob Storage 1 and click Next at the bottom. Now I have Choose the Input File or Folder. Under File or Folder, I'm going to click Browse on the right. And now I'll choose my source input, so Source Folder. I'll click Choose at the bottom. Under File Loading Behavior, I'm going to choose Incremental Load Time Partition Folder File Names. Now if I go back up to File or Folder, I have some details about variables. So what I'm going to do is I'm going to add to my file or folder path source / and then in curly bracket year / in curly bracket month / in curly bracket day / in curly bracket hour. That's the folder structure that it should figure out at runtime as to which folder to look under. So if I scroll down, there's some other options. There's a binary copy. I'm going to check that because I'm just going to do a binary copy of the file. I'm also going to check delete files after completion because we're not actually going to copy, we're actually going to move is the official thing we're going to do. So I'm going to click Next at the bottom. Now we're at Destination Data Store. It's the same data store, so just check Azure Blob Storage 1 and click Next at the bottom. Now choose the output file or folder. So under folder path, I'm going to click in the text box and I'm going to type sync / and then in curly bracket year / in curly bracket month / in curly bracket day / in curly bracket hour. So we're going to put it in the same folder structure. And then a / after hour. That's very important. Okay, and now that I think about it, I'm going to back up because I believe I left the / off. I just hit previous button twice to back up to the choose the input file or folder. And under file or folder, I'll add a / on the file or folder. That's very important because otherwise it thinks that the hour is the name of a blob and not part of the actual folder structure. So I went back twice. So I'm going to click Next and then Next again. And I'm back to choose the output file or folder. I'll make sure there's a / on that. I'll click Next. Now under Settings, I'm just going to leave all of this defaulted and click Next. And now we're on the summary. So it's going to copy from blob storage to blob storage. So I'll click Next. So now it's going to validate and set everything up. Okay, that's complete. So I'm now going to click Monitor at the bottom of the Copy Data tool. And we're able to watch our pipeline run. So let's go back to Azure for a moment. And I'm going to click Home at the top left of my Azure. And in my recent resources, I'm going to click my storage account. Now on the right, in Overview, I'm going to click Containers. And I'm going to click my sync. You see now under my sync, I have a folder that says 21, which is the year 2021, 04, which is the month if I click on it, April. If I click on that, there's the day, the 15th. If I click on that, the hour is 21, and if I click on that, there's my test.txt. If I click on storage 2256, my storage account at the top left of the screen, takes me back to my containers. And in my container list, if I click on source, I now have nothing in there. So having this set up, it will trigger every 5 minutes, and it will move any files that were in the folder for the last hour incrementally to the sink. In this video, I'm going to be discussing analytic data stores. In a big data environment, there are data pipelines with stages that store different types of data. There's typically a data store, for example, that stores unprocessed raw data as it enters the environment. There may also be intermediate stages. Once the data is finished being processed, it goes to an analytical data store which stores processed data. This data has specific structure. It's been prepared to be queried by analytics tools. So in other words, analytics data stores represent the final destination of data pipelines before either presentation or higher level analytics processing. Analytical data stores are part of what's called the serving layer, or the layer that serves data. In this video, we'll break the serving layer down into its constituent parts. Serving layer processing can be broken into two parts. The speed serving layer, also called the hot or real-time data path, is the layer that serves data immediately as it comes into the system. This might be used, for example, by a chart that's being updated real-time, showing the instantaneous power output of wind turbines. This data is coming in incrementally. It's not meant to be processed in large blocks of time, but rather immediately as it comes in. The idea with the speed serving layer is speed over accuracy. Perhaps a given value might be made more accurate if it's averaged with the data that follows it. But with the speed serving layer, all you have to work with is the immediate data and perhaps a small window of previous data. The latency on the speed serving layer is usually seconds or even sub-second. The other layer is the batch serving layer. This layer focuses on accuracy over speed. Processes in the data pipeline might have processed large batches of historical data to come up with aggregates and other output that makes up the batch serving layer. The latency on batch output may be minutes, hours, and in some cases even days. AI and machine learning systems might consume the batch serving layer to learn patterns in the batch data over time. The serving layer has the following read-write requirements. Both the speed and batch serving layers should support low-latency random reads. A random read is a read that requires a search through the data. Both types of serving layers need to support the consumer's need to read data quickly in a non-sequential manner. The speed layer has the additional requirement of random writes, or the ability to write any number of bytes of data at any given time. The speed layer needs this because speed is of the essence, so the layer can't wait until a certain batch size of data has arrived before writing it. To put this in a real-world context, if you're watching a real-time trend, you want it to update near real-time, not every 10 minutes or so when a certain batch of data has arrived. The batch layer, on the other hand, only needs to support batch writes or appending batches to the end of the data store. Because nobody's waiting for real-time data to arrive in the batch layer, a longer latency is expected. Here are some analytical data storage options offered by Microsoft Azure. Azure Analysis Services is a tabular analysis storage largely compatible with SQL Server analysis services. Azure Cosmos DB is a globally scalable NoSQL store that offers guaranteed throughput. Azure Data Explorer has its own unique query language to allow real-time analytics on data such as time series data. Azure SQL Database acts as a scalable SQL database in the cloud. Azure Synapse Analytics combines enterprise data warehousing and analytics for big data. HBase for HD Insight and Phoenix, which essentially adds a SQL interface to HBase, is a NoSQL solution built on the Apache Hadoop technology. Hive LLAP is an HD Insight cluster type that allows for more efficient querying of stores such as Apache Hive. And finally, you can host a SQL Server instance in an Azure virtual machine on the cloud. All of these can be used as data serving storage for analytics. Various data store databases support different data models. A key value model means that each record in the database consists of a unique key for lookup and an associated value. If you have a lot of data and your query needs are basically to query by a single key, then key value is a very performant choice. Document databases store documents such as JSON, CSV, or XML. The fields in the documents can be queried. A column family database is a type of key value database where the value is a column of data. The key represents objects, and columns or attributes related to the object can be grouped and partitioned for easy access. It allows specific columns of information to be retrieved without retrieving the entire object. Graph databases store mathematical graphs, which consist of nodes and edges or vectors which attach those nodes. Logically, a node represents an object, and an edge represents the relationships between objects. Queries are called traversals over the graph to find information. It's good for data that has many complex and dynamic relationships between objects. For instance, you could have a graph that contained people in a company and their professional relationships. And you could query for all employees who work under Bob at any level of the organization. And finally, there's telemetry and time series data. This data is append only and contains timestamped or temporal data. It's often used in relation to Internet of Things services, or in other words, data collected from physical objects, since readings from physical objects have a collection time associated with them. When you're selecting a data model to use, ask yourself the following questions. Does storage need to be hot path? In other words, are you looking for real-time data? This will narrow your options, since you'll need a low latency solution, whereas with cold path, you're less concerned about latency. Are your needs relational? SQL Server is a great option for relational data, or when your data objects have a rigid relational schema. If there are little or no relationships required between your objects, then a NoSQL solution such as Cosmos DB might be more suitable. Do you require massively parallel processing? For example, if you're reading real-time data from thousands of autonomous cars, each sending sub-second data to your solution, you might need to perform massively parallel processing to keep up. Only certain data stores handle such processing. And is your data time series? If so, then you might want an append-only data store designed for such data, such as Azure Data Explorer. In this video, we're going to look at external data stores used with HD Insight to store metadata. Metadata refers to schema, like schema in a SQL Server database. It contains table structures, relationships, etc. Apache Hive Metastore supports this ability to store its metadata externally, as does Apache Uzi Metastore and Apache Ambari database. The external Metastore option we'll look at is applicable to any technologies that can run Spark clusters with Apache Hive Metastore, such as Azure Synapse Analytics and Azure Databricks. The features of an Apache Hive external Metastore are: they use an Azure SQL database under the hood to store the metadata. They store the central schema repository for the Hive database, such as table structures and table relationships. The metastore that defines the schema for the Hive database is then accessed by the big data tools that access the Hive database, such as Apache Spark. There are two options for setting up a Hive external metastore. The default Metastore is created and managed automatically with the Hive database, and a custom Metastore is defined and managed by the operator setting it up, independently of the Hive database. We'll look at how these work in more detail in the following slides. First, let's look at the default Metastore. Each cluster comes with a default Metastore. This default Metastore is managed along with the cluster itself. It's created when the cluster is created and deleted when the cluster is deleted. Therefore, it doesn't support any metadata that requires usage outside the lifecycle of the cluster itself. Because it's created and destroyed with the cluster, a default Metastore can't be shared with other clusters. In other words, its scope is a single cluster. The default Metastore is fine for simple workloads that only require a single cluster. If you have a more complex workload involving multiple clusters, and if those clusters need to share metadata or schema, then the default Metastore is not going to be enough. But one nice detail of the default Metastore is that it doesn't cost anything. It's included free of charge with the cluster. One use case that comes immediately to mind for the default Metastore is testing or experimenting scenarios, where only a single cluster is required and the workload, being a test workload, is not heavy. This will save time and money over having a custom Metastore. A custom Metastore, on the other hand, is not a physical part of the cluster like the default Metastore is. Rather, it stores the schema or metadata in an external Azure SQL database. A custom Metastore allows multiple clusters of different types to attach to the same Metastore. In other words, the Metastore is not scoped to a single cluster. The lifecycle of the Metastore is not tied to the cluster lifecycle. This means that it's up to the operator setting up the Hive database to also implement the Azure SQL database and configure the system such that one or more clusters are using it. When clusters that are using the Metastore are deleted, the Metastore, which is actually an Azure SQL database instance, is not automatically deleted. It needs to be explicitly deleted. Where a default Metastore is free, a custom Metastore has a cost associated with it, which will be the cost associated with whichever Azure SQL database instance the operator sets up to be the Metastore. It's a rule that the cluster or clusters using a Metastore need to be hosted in the same region as the Metastore. This is to help with latency and performance. A default Metastore has a set size, but custom Metastores have the ability to be scaled up. Essentially, this takes advantage of Azure SQL database scalability. So in summary, a custom Metastore enables the flexibility for complex processes using multiple clusters by allowing multiple clusters of different types to share a Metastore, and allowing that Metastore to scale along with the process. It has some overhead in management, since it doesn't share a lifecycle with a single cluster, and it also has a cost associated with it, which will be dependent on its usage. So in this course, we've examined how dimensional modeling and hierarchies are used in data storage, and how the schema can affect performance. We did this by exploring dimensional data modeling and hierarchies, slowly changing dimensions and designing a database for temporalness, star and snowflake schemas and designing a star schema, implementing incremental data loading using Azure Data Factory, and choosing an analytical data store and Metastore design. In our next course, we'll move on to examine how to plan and implement an efficient physical data storage structure.